Welcome back. In the last video we finished up calculating the right hand side. Since we already have a procedure for solving the Poisson equation, we are now able to find the pressure. We can also calculate the gradient thanks to this function that we made a couple of videos ago. So we can even calculate what's over here. And I think in this video then we will start looking at this term. But before we do that, I want to make a new procedure that I call index. And it's gonna, this Copilot is gonna take a row which has some type, let's say int in that column, and also a stride. It's gonna return an int. But the most important part is that, or not the most important part, but a small optimization is that we force it to be inline. Then we simply return row times stride plus column. And that will make these expressions a little bit nicer, I think. Let's have a width up here. And we don't use semicolon, I keep forgetting. Then we'll use that as the stride. And here we'll have index row column -1. And similar here, the rest. So let me cut ahead. Alright, so I changed something. I was writing this all the time. And width never changed. Right, and that was annoying me a little bit. And in any other language you would make a closure. But closures that capture local variables, they don't exist in Odin. So what you can do instead is you can use the context. And the context is something that's implicitly passed to all function calls. And it contains these things. And all of this is kind of useful. This is internal use only. And it has this pointer. So what I did was use this point. Maybe I could also use the user index, but you can put any data inside this raw pointer. So I put the address of the width, which I'm using as the stride. And inside the index function, I just dereference that pointer. And that way I can kind of capture a variable without really capturing a variable. And now I can just write the indexing like this, which is a lot nicer to read. But this function call is then a bit weird, but that's fine. And if we try to run it, it actually runs. So it compiles and everything. Right, so what we were talking about was this operator. So let's try to write out what it is. I'm going to do it here. So we have v c dot nabla on v. So the first thing we gotta get is this thing, which is vx nabla x plus vy nabla y. And then this equation has two components. So let's look at the x component first. It's this operator applied to vx, and same thing for the y component, except it's y over here. So that is not too bad. Let's think about how we can calculate that. So we'll need some kind of procedure I'm not sure what this term is called. Let's just call it let's call it the floop, or I don't want to call it flux because it actually means something. I was trying to come up with some kind of nonsense word. Let's call it just the fluid term 1 until I find out what it's actually called. So there are two components we want to calculate. So let's call them x, and it can be just a field, and y, and we don't return anything. But to calculate these things, we need the velocity and the velocity in the other direction. So what I would actually also like is to have some scratch fields, because what I want to do now is to call not fluid, but let's put it inside field for some reason, is to call this gradient function. But as you can see, it takes a field. So let's say we call it on the x velocity, because we need that gradient here. We have both components there. Then we need two destination fields. And we cannot use these destination fields because they need to contain the final data. We can't use the input fields, of course. So for now, let's have two scratch fields. Which we will then use here, scratch 1 and scratch 2. And they then contain scratch 1, 2 now contains a gradient in xy direction. Great. And then we can say, the problem is we have to loop over the fields. Okay, let's do it a simple way first. So for rho in 0 to height minus 1, or like this. For column 0 to width. Then we can say context user pointer equals the address of the width. And then we can actually use this index function we just built. Then we can say here index row column should be equal to, and I guess it's data. Yes, it's called data. Data at that. You know what? We could even just call it once. So this thing times scratch 1 at IDX plus this thing, and actually that one has to be data as well, and this one has to be data. Right. No, I didn't mean to do that. And scratch 2. So now we've filled up that one. Now we essentially do the same thing, but for Vy. And I suppose we can say Vx is now Vy. Although not quite. This one has to be Vx still. And actually that's almost it. Now we should be done. These kind of scratch fields are kind of proliferating because I don't want these functions to allocate any memory. We're gonna call them a lot. They shouldn't be allocating memory. We should allocate memory once and then just reuse that memory. So we need this kind of structure. Could also be passed through the context, but I think it's a little bit clearer if we do it like this. So even though it's not super pretty to have all these fields, I guess that's how we're gonna do it. So I think we're gonna call it here for this video, even though it was short by my usual standards. We haven't really tested this, but then again, there's not a super good way. Let's test if it compiles. So it does compile. But yeah, let's leave it here, and then in the next video we are actually going to put everything together and try to do some fluid dynamics. So until then.